So up to now, we have uh, studied or seen the signs of polarization. So what is polarization we saw? What is polarization vector we saw? Then we saw the general equation for polarization vector that gives us a generalized ellipse. Then we saw special cases of that ellipse. One special case is a straight line, which can be horizontal or vertical. Then another special case is an ellipse, whose major axis is along the horizontal axis, or the major axis is along the vertical axis, either the horizontal axis or the vertical axis. Then we saw the third special case as a circle, and we saw under which circumstances it can become a straight line or an ellipse or a circle, and what will be the sense of polarization if it is an ellipse or a circle. So all those things that we have discussed up to now. Now from now on, let us look at the technology or techniques involved in the polarization. So to know that, we'll start with the measure of polarization. So how do you going to measure the polarization? Now in the polarization, we have seen on the polarization vector is given by an equation which is the equation of an ellipse. Now when we say polarization vector, it is a vector of the wave. So we have the wave which is giving us the ellipse, Since it is giving us the ellipse, we have to, this wave is generating an ellipse. The tip of the electric vector in the wave is generating an ellipse. So we can describe this parameter in terms of an ellipse. So giving an ellipse, we can be given an ellipse, and we will be asked to design a system which gives us polarization which resembles this ellipse. Now this is for the parameters of the ellipse are called the elliptical parameter or ellipse parameter or the wave parameters. Because the wave describes an ellipse, therefore it is called the wave parameters. Now what are these parameters? The parameters are the tilt angle, which is the tilt of the major axis with respect to the horizontal axis or the x-axis. Now what will be the range of this? What will be the range of this tilt angle? That is, now look at this ellipse, the figure. Now the tilt angle, when tilt angle is equal to 0, the tilt angle is, the semi-major axis is along the x-axis. Now if we keep on increasing the tilt angle, so it will move from 0 to pi by 2 when this tilt angle, the semi-major axis, will be along the y-axis. Then if we further increase it, it will keep on moving towards the x-axis. Again, from the y-axis, the semi-major axis will be again along the x-axis. So from x-axis, semi-major axis, from x-axis to y-axis, then to x-axis. Then from that, if we again further increase, there is no point in increasing that because it will be again repeated. So from the x-axis, it will go to y-axis, then come back to x-axis. So there is no point in further increasing the tilt angle. Everything about the ellipse, all the knowledge can be obtained if we move the tilt angle from 0 to 180 degree or pi. So therefore, the range of the tilt angle or the limit on the tilt angle is 0 to pi. So 0 will be less than equal to tau, will be less than equal to pi, where tau is the tilt angle. Then the other parameter is called the axial ratio or AR. Axial ratio is the ratio between the two axes. There are two axes in the ellipse. One is the semi-major axis, other is the semi-minor axis. So the ratio between the semi-major axis and the semi-minor axis that is defined as the axial ratio of the ellipse. So the axial ratio for a circular polarization, we will have A is equal to B, semi-minor axis and semi-major axis are same. Therefore, axial ratio is equal to 1. If we have a circular polarization, axial ratio is equal to 1. So for circular polarization, A is equal to B or axial ratio is equal to 1. So major and minor axis are equal. So AR is equal to 1. Now the other extreme case is linear polarization. In the linear polarization, it has to be a straight line. So we'll take the larger straight line, which is the major axis. So in that case, the minor axis has to vanish, which means B is equal to 0. If B is equal to 0, we get the linear polarization. In general, we get the linear polarization. Same thing. You can say A is equal to 0. That also gives us linear polarization. We'll take B is equal to 0. Either of these two will give us linear polarization. We'll take B is equal to 0. Why? Because B actually represents the bulge of the ellipse. If we have seen the ellipse, it is oriented along the major axis and there is a bulge along the minor axis. So the bulge is given by the minor axis B. So when there is no bulge, it is only a straight line, it is B is equal to 0. So linear polarization for B is equal to 0. If B is equal to 0, then minor axis vanishes and AR, which is equal to axial ratio, is equal to A by B. B is equal to 0, so AR is equal to infinity. If we take A is equal to 0, A is equal to AR is equal to 0. So AR can be 1 for circular polarization, AR can be 0 or infinity for linear polarization. Now AR is equal to 0 is not important here. The reason is 0 is between infinity and 1. So therefore now we can find out what is the limit of AR. The limit of AR is between 1 and infinity. So a minimum value will be obtained when we get circular polarization. So that is 1. That is less than equal to AR is less than equal to infinity. If it is infinity, it is a linear polarization. In between 1 and infinity is equal to 0. So when AR is equal to 0, again it is linear polarization. So that is not the limit. Limit is infinity. So 1 less than equal to AR less than equal to infinity. So these are the wave parameters. What are the wave parameters? Tilt angle and axial ratio, or A and B. So these are the wave parameter or parameters of the ellipse described by the wave. When we go for the design of a system for a particular polarization, then we require these wave parameters. These are described. These are given to us. This will be the tilt angle. This will be the axial ratio. Design a system for this. So the wave parameters are useful in designing a system, because the system will be required to give us this ellipse, the particular ellipse which has this tilt angle is fixed, AR is fixed, axial ratio is fixed. And then when we come to this axial ratio, tilt angle has no convention, but the axial ratio, that we include a convention. We say that it is from 1 to infinity, but there is a sense of polarization. Either it is left hand polarized or it is right hand polarized. So there is a sense of polarization. To take care of the sense of polarization, some convention is used. The convention is this. It is called right hand polarized. If the AR is positive, it is called left hand polarized if AR is negative. So now we have already seen AR is positive because it is between 1 and infinity. Now we are saying it is positive, AR gives RHP, and negative AR gives LHP. How is it possible? And now you can know from here that actually we are considering the absolute value of AR. So 1 less than equal to absolute of AR less than equal to infinity. Now this AR actually is between 1 and infinity. As a convention we are taking, if we are describing a RHP, we are considering positive AR. If we are considering LHP, we are considering negative AR. So L for LHP, it will be -1 less than equal to AR less than equal to -infinity. So that is, sorry, -infinity less than equal to AR less than equal to -1. That will be for LHP by convention. So it is only a convention. So this is about wave parameter. Then we have the electric components. So the wave has electric field. So electric field has two components. One is E1, other is E2, or one is EH, other is EV, with a phase difference delta between them. Therefore, when we have got an elliptical polarization, so this is not design, now the analysis. So we have got an elliptically polarized wave. If you have got an elliptically polarized wave and you are going to analyze that elliptically polarized wave, then you require the electrical parameters. Electrical parameters are the components and the phase difference between the components. So how we define the electrical parameters now? We have defined the wave parameters or the ellipse parameters. Now we are going to define the electrical parameters, which is very simple. The electrical parameters is, the first parameter is E2 by E1 or E1 by E2, either of these two. So on the first parameter is the ratio of E2 by E1. E2 and E1, the ratio of E2 to E1 is one electrical parameter. So if we know what is E2, it is E1, we can find out that ratio. So that is one electrical parameter. Then the other electrical parameter is delta, and delta is the phase difference between E2 and E1. As you know, the phase difference between B can be between 0 to pi or 0 to 180 degrees. So 0 to pi, instead of writing 0 to pi, if we want to take care of the sense in describing the phase difference, then we can write it as minus pi by 2 is less than equal to delta is less than equal to pi by 2. Minus pi by 2 to pi by 2, the total phase difference is 180 degrees, which is same as 0 to pi. So instead of writing 0 to pi, we write it from minus pi by 2 to less than equal to delta less than equal to pi by 2. When delta is greater than minus pi by 2 is negative, then we call it LSP. Delta is positive, we call it RSP. That way we define it. Now if you look at these definitions, then you can see that we have two angles. In the first definition we have got a tilt angle. In the second definition we have got a delta phase difference, which is an angle. So we have got angles in both the definitions. Then in both the definitions we have got a ratio or number. In the first definition it is axial ratio, which is a number. In the second definition we have got E2 by E1, which again is a number. So there is a discrepancy here. The discrepancy is, it is angle number, angle number. Either it should be number or it should be angle. That will be easier to do the design or the analysis if we have everything in terms of angle or everything in terms of number. Let us try to do that in terms of angle. So measure of polarization as angles, not in terms of number. So numbers will eliminate, we will try to eliminate the numbers and concentrate only on angles. So measure of polarization as angle. So let us start with this wave parameters. That gives us the measure of polarization. So in the wave parameter we have tau, which has an angle. Then we have axial ratio, which is a number. And now any number can be related to an angle. So for example, sine theta is equal to a number. Take any angle, theta is an angle, sine of theta is equal to a number, or cot theta is equal to a number, or theta is equal to cot inverse of that number. So number and angle are related. So let us use that concept. So here what we'll do is tau is an angle. Then we look for another angle which is epsilon. So we'll write epsilon, define epsilon as epsilon equal to cot inverse of plus minus AR. Why plus minus AR? We have defined AR to be positive or negative to describe the sense of polarization. So if it is plus AR, then epsilon is equal to cot inverse AR. That gives us the positive RHP. Similarly, epsilon is equal to cot inverse minus AR. That gives us the LHP, left-hand polarization. So these two polarizations. For that we use so from this we get angles. Now tau is an angle, epsilon is an angle. So we have got two angles to describe the wave parameter. Now let us come to describe the electrical parameters in terms of angles. In the electrical parameter, one angle is delta, that we know. For the other angle, let us use tan. So we'll have delta and gamma. Gamma is equal to tan inverse E2 by E1. So delta is one angle, other angle is gamma. Gamma is equal to tan inverse E2 by E1. So this is how we can measure the polarization. Measure of polarization can be taken in terms of angles. For wave parameters, the angles are tau and epsilon. For electrical parameters, the angles are delta and gamma. These are all these measures, the polarization, etc., that we are doing in space. As you know, space is a 3D graphic. So since space is particularly 3D, and you know space is curved in nature, therefore these will be following the geometry which is not linear geometry, which is curved. It is not Cartesian coordinate system, it is curved geometry. So in that case, what will be the relationship between the wave parameters and electrical parameters? So can we convert electrical parameter to wave parameter? The answer is yes, but the conversion is not within the scope of our discussion. Similarly, can we convert wave parameters to electrical parameter? Answer is yes, but it is again not within the scope of our discussion. But what is within the scope of our discussion is the final conversion formula. So let us look at the final conversion formula. Start with electrical parameters to wave parameters. What are the electrical parameters? Delta and gamma. What are the wave parameters? Tau and epsilon. Which means electrical parameters to wave parameter conversion means we will describe tau in terms of delta and gamma. We will describe epsilon in terms of delta and gamma. The expressions for that are cos 2 gamma is equal to cos 2 epsilon into cos 2 tau, and tan delta is equal to tan 2 epsilon by sin 2 tau. So this is electrical to wave parameter conversion. Similarly, wave to electrical parameter conversion is tan 2 tau is equal to tan 2 gamma into cos delta, and sin 2 epsilon is equal to sin 2 gamma into sin delta. So please note it down. I will give you a moment, 1 minute or 2 minutes. Please note it down. Then we will proceed further. Please note the conversions. Okay, and now what we have seen is what is the limit on tau, what is the limit on delta, that we know, those the limits we have seen. Then what is the limit on AR and what is the limit on E2 and E1, that we have seen. Now if we know those limits, then we have to find out what are the limits on tau and epsilon, what are the limits on delta and gamma. So range of the angles. So let us find out what will be the range of the angles. For tau we have seen the range is from 0 to pi. We can go beyond pi, but that is again repeating the ellipse. So there is no point in going beyond pi. So tau is between 0 to pi. 0 less than equal to tau less than equal to pi. Because if we go beyond pi, the shapes are repeating, so there is no point in going beyond pi. This we have already discussed, we have already seen. Then for epsilon, epsilon is equal to cot inverse of plus minus AR, where 1 is less than equal to AR is less than equal to infinity. AR is axial ratio. Therefore, if we put these limits on AR, so AR will be plus minus 1, because cot inverse of infinity plus minus infinity will be plus minus 1. So since AR will be plus minus 1, when we put AR is equal to plus minus 1, epsilon is equal to plus minus pi by 4. So epsilon AR is equal to 1 gives us epsilon is equal to cot inverse of 1, which is pi by 4. AR is equal to minus 1 gives us epsilon is equal to cot inverse of minus 1, which is pi by 4 minus pi by 4. Between these two regions will be the cot of infinity. Cot of pi by 2 will be from cot of minus pi by 4 to plus pi by 4. That will include cot of pi by 2 and 0, which will give us AR is equal to infinity. So AR is equal to infinity, which means epsilon is equal to 0. And these two are the limits. So 0 remains between plus pi by 4 to minus pi by 4. Therefore, the limit on AR, epsilon, is from minus pi by 4 less than equal to epsilon less than equal to pi by 4. So the two limits we have found out. 0 less than equal to tau less than equal to pi is the limit on tau, or the tilt angle. Then minus pi by 4 less than equal to epsilon less than equal to pi by 4 is the limit on epsilon. That takes care of AR is equal to plus minus 1 and AR is equal to infinity, because AR is equal to infinity corresponds to epsilon 0. Epsilon is equal to 0 is between minus pi by 4 and pi by 4. Similarly, AR is equal to 1 or minus 1 correspond to epsilon is equal to plus or minus pi by 4. So both these limits we have found out. Now let us look at the limit on delta, or the phase difference between E1 and E2. Delta is the phase difference between E1 and E2. So that we write the limit is 0 less than equal to delta less than equal to pi, but for considering the polarization sense, we write this as minus pi by 2 less than equal to delta less than equal to pi by 2. This we have already discussed. For minus pi by 2 to delta, or minus pi by 2 to 0 is for left hand, 0 to pi by 2 is for right hand. So this we have already discussed. Then gamma is equal to tan inverse E2 by E1. If gamma is equal to tan inverse E2 by E1, then on the limit on gamma will be from 0 to pi, because so you will get, because tan inverse E2 by E1, the limit on tan inverse E2 by E1 is from 0 to pi. So if we put that limit, it will be 0, which is less than equal to gamma or less than equal to pi. So this is the discussion on a range of angles. So what we will do is we will stop here This is about polarization, discussion on polarization, measure of polarization, and range of the measure on polarization. So everything we have covered about polarization. So we'll stop here for today. If you have doubts or if you have any questions or comments, I will be happy to answer that. And let me tell you something else. What I discussed or what we discussed today, you may not get it in your textbook. The described textbook does not give this. The discussion that we made today is not available in your prescribed textbook. So you can look at my YouTube channel for this.